Hi everyone, and now we are going to talk about decision trees. My name is Stanislav Yeroshenko. I represent Ural Federal University, and within the context of our today's lecture, we'll be focusing on decision trees, actually the basic concept, what is a decision tree. Finally, we'll move to ensemble methods, so how decision trees can be effectively combined to produce more effective and more accurate solutions. So we'll consider the concepts of boosting and bagging. And well, I think that it will be really useful for you to see in figures on how a regression tree could be calculated based on the solar irradiation data of photovoltaic power plant. So we start with the basic background of decision trees. Actually, a decision tree is a decision support tool that uses a tree-like model of decisions and their possible consequences, including chance, event outcomes, resource costs, and utility, whatever. So it is one way to display an algorithm that only contains conditional control statements. Decision trees are commonly used in operation research, specifically in decision analysis, to help to identify a strategy most likely to reach a final goal. But actually, decision trees are also a popular tool in machine learning. A decision tree is a flow chart-like structure in which each internal node represents some sort of a test on an attribute. For example, whether a coin flip comes up, heads, or tails. Each branch represents the outcome of the test, and each leaf node represents a class label, decision taken after computing all the attributes. So, the path from root to leaf represents classification rules. The decision tree can be linearized into decision rules, where the outcome is the contents of the leaf node and the conditions along the path from a conjunction, like if there are any clause. In general, the rules have the form. So if condition 1 and condition 2 and condition 3, so then we have some sort of the outcome. Decision trees and decision rules can be generated by constructing association rules with the target variable on the right. They can also denote temporal or causal relations. Well, now let's talk a little bit about decision trees' advantages. Among decision support tools, decision trees have several advantages, and actually, first of all, they are very simple to understand, and it is very simple to provide interpretation of the outcome. People are able to understand decision tree models after a very brief explanation. Important insights can be generated based on experts describing a situation and their preferences for outcomes, like alternatives, probabilities, costs, whatever. Decision trees help to determine worst, best, and expected values for different scenarios. Moreover, they use some sort of a white box model. So if a given result is provided by a model. Moreover, decision trees can be combined with other decision techniques to make more powerful, more strong decision support systems. Well, being more specific about the disadvantages of the decision trees, I would say that this sort of mathematical approach is unstable. So, meaning that a small change in data can lead to a large change in the structure of the optimal decision tree. Moreover, they are often relatively inaccurate. So, many other predictors perform better with similar data sets. This can be remedied by replacing a single decision tree with an ensemble, like a random forest of decision trees. But a random forest is not easy to interpret as a single decision tree because at each step you may have thousands of decision trees together. For data including categorical variables with different number of levels, information gained in decision trees is biased in favor of those attributes with more levels. Calculations can get very complex, particularly if many values are uncertain and if many outcomes are linked between each other. Well, now let's focus on the methodology that is more likely to be applied for your summer school project case. And these are the ensemble methods. So, actually, we have a pretty good understanding of what is a decision tree, yes, and what are the advantages and disadvantages of simple decision trees. And now we'll talk about what makes them such a good base estimator for ensemble methods. Some of the most popular ensemble methods based on decision trees are random forest, bagging, adaptive boosting, gradient boosting, extreme gradient boosting, etc. So all of these ensemble methods take a decision tree and then apply either bagging, bootstrap aggregating, or boosting as a way to reduce variance and bias of the model. Well, random forests focus on implementation of bagging procedure. And actually, random forests are an ensemble learning methods which can be used for classification, regression, and other tasks that operate by constructing a multitude of decision trees at training time. For classification tasks, the output of the random forest is the class selected by the majority of trees. For regression tasks, the mean or average prediction of the individual trees inside the forest is returned. So, random decision forests correct for decision trees' habit of overfitting to their training set. So, random forests generally outperform decision trees, but their accuracy is typically lower than gradient boosted trees. However, data characteristics can affect both the performance of decision trees, random forest, and gradient boosting as well. The training algorithm for random forest applies the general technique of bootstrap aggregating or bagging to simple, weak tree learners. So bootstrap aggregating, also called bagging, is a machine learning ensemble meta algorithm designed to improve the stability and accuracy of machine learning algorithms used in statistical classification and regression. It also reduces variance and helps to avoid overfitting. Although it is usually applied to decision tree-like methods, it can be used with any type of method. Bagging is a special case of the model averaging approach. So before we get to more detailed explanation of bagging, let's take a quick look at an important foundation technique called the bootstrap. So the bootstrap is a powerful statistical method for estimating a quantity from a data sample. So this is easiest to understand if the quantity is a descriptive statistic such as a mean or a standard deviation. So let's assume we have a sample containing 100 values of variable x, and we'd like to get an estimate of the mean of the sample. We can calculate the mean directly from the sample as dividing the sum of all the variables in the data set by 100. Actually, 100 is the total number of the variables in the data set. We know that our sample is small and that our mean has an error in it. So we can improve the estimate of our mean using the bootstrap procedure. So let's create many, let it be 1000, random sub-samples of our data set with replacement, meaning we can select the same value multiple times. Then we calculate the mean of each subsample, then calculate the average of all of our collected means and use that as our estimated mean for the dataset. For example, so let's say we used 3 resamples and got the mean value 2.3, 4.5, and 3.3. Taking the average of these, we would say that the estimated mean of data would be 3.3 as well. So this process can be used to estimate other quantities like standard deviation or even quantities used in machine learning algorithms like learned coefficients. In machine learning, boosting is an ensemble meta-algorithm for primarily reducing bias and also variance in supervised learning. And it's like a family of machine learning algorithms that convert weak learners to strong ones. While boosting, it is not algorithmically constrained. Yes, most boosted algorithms consist of iteratively learning weak classifiers with respect to a distribution and adding them to a final strong classifier. When they are added, they are weighted in a way that is related to the weak learner's accuracy. So after a weak learner is added, yes, so the data weights are adjusted, known as reweighting. Misclassified input data gain a higher weight, and examples that are classified correctly lose weight. Thus future weak learners focus more on the examples than previous weak learners misclassified. AddiBoost, short for adaptive boosting, is a statistical classification meta-algorithm. It can be used in conjunction with many other types of learning algorithms to improve performance. The output of the other learning algorithms, weak learners, is combined into a weighted sum that represents the final output of the boosted classifier. So AddiBoost can be called adaptive in the sense that the subsequent weak learners are tweaked in favor of those instances misclassified by the previous classifiers. In some problems, it can be less susceptible to overfitting problem than other learning algorithms. The individual learners can be weak, yes, but as long as the performance of each one is slightly better than random guessing, so the final model, which is considered as an ensemble of weak learners, can be proven to converge to a strong learner and provide more effective and accurate solution. Gradient boosting is a machine learning technique for regression, classification, and other tasks, which produces a prediction model in the form of ensemble of weak prediction models. Typically, it is used for decision trees. When a decision tree is the weak learner, the resulting algorithm is called gradient boosted trees, which usually outperforms random forest. Gradient boosting has three main components. First one is the loss function. The role of the loss function is to estimate how good the model is at making predictions with the same given data. This could vary depending on the problem at hand. For example, if we are trying to predict the weight of a person, depending on some input variables, then the loss function would be something that helps us find the difference between the predicted weights and the observed weights. On the other hand, if we are trying to categorize if a person will like a certain movie based on the personality, we'll require a loss function that helps us understand how accurate our model is at classifying people who did or did not like certain movies. So, weak learner is the second important concept associated with gradient boosting algorithm. So it's actually it's the substance that classifies our data, but it does it really poorly. So perhaps no better than random guessing. In other words, it has high error. These are typically decision trees, also called decision stumps, because they are less complicated than typical decision trees. And the third important component is the additive model. So this is the iterative and sequential approach of adding trees, weak learners, one step at a time. After each iteration, we need to be closer to our final model. In other words, each iteration should reduce the value of the error, the value of the loss function of the previous one. So, as far as we consider the basic concepts of using ensemble algorithms, I would like to focus your attention on a numerical example on how to build a decision tree, because this numerical example, at least from my point of view, provides a better understanding of the algorithms dealing with decision trees, and like moreover and more likely with ensemble algorithms based on decision trees. Okay, so first of all, let's consider creation of the regression tree with 3 levels. Yes, so the creation of regression tree with 3 levels looks like this. Yeah? It's level 1, 2, level 3. Okay, so we have a data sample and a feature which we use to forecast, to predict the output is solar irradiance at the border of the atmosphere, so it's G0. And the output is measured solar irradiance, which is actually measured at the photovoltaic power plant by means of the installed pyranometer, yes, so the special device used to measure the solar irradiation. The data set is provided in the table, and well, for the purpose of simplicity, let's use the data set only for 1 day, and objects of the data sample are depicted as and plotted in the corresponding axis at the left side of the slide. Actually, you may see that the averaging step is 30 minutes. So it means that for 1 day, we have approximately 48 measurements, which corresponds and form our initial data set. Okay, so objects in the data sample are depicted in the plot in G0 and GM axis. So G0, let me remind you, is actually the feature that we are using. It's irradiance at the border of the atmosphere. And GM, actually, it's a measured value. So in order to make the calculation process more transparent and understandable, let's eliminate night hours out of the training sample, because, well, even from practical point of view, we are not really supposed to provide the photovoltaic power plant's forecast for night hours, because it's purely understandable that at night PV power plant doesn't work because we do not have the sunlight. Well, now we have the reduced data sample composed only of the features and outputs related to the daytime hours. So the picture of the graph, the charted diagram of the measured irradiance, is presented at the left side of the slide. Well, now let's assign a serial number to the objects in the dataset. It's here. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. At this stage, following the procedure of gradient boosting, for instance, we initiate the basic algorithm. So it's like B0. Yep, B0. And as far as it is the first basic algorithm, so B0 of x, so it equals 0. As far as it is the first algorithm, the composition of the algorithms equals to 0 as well. So we have actually A of x equal to 0 as well. Okay, let's move forward. In order to build the decision tree, let's sort feature x from minimum to maximum and redesign the table. So we use feature x, and sort from minimal value to maximum value. So we have changed the order, of the numbers, and correspondingly changed the output variable as well. Okay, so For sorted values, we need to calculate the shifting vector. For output 1, so it's y1, and 0 composition of x1, so we get 17.044. And actually, this shifting vector has such mathematical formulation as far as it can be treated as a derivative of the anti-gradient function. Yep. A derivative of the loss function used for our algorithm. So it's represented in such mathematical formulation. So similarly, the other values of the shifting vector are calculated. It's like S2, S3, S4, etc. Let me draw your attention to that after filtration, we have only 17 entries in our data sample. Well, don't be afraid, like too many formulas. Based on the shift vector S1, let's try to divide the sample containing L entries into two parts. As far as we have binary decision trees, yes, so let's do it. So we have L-1 possible ways to divide the sample into two parts. And the first way is like to take just 39 to the left part, yes, and to take this vector to the right part. So the second possible division is provided here. So we take two first variables, yes, and the right part contains the rest of the data sample without these two first values of the feature. Actually, we have L-1 possible ways to divide the sample into two parts, yes, and actually, let's move forward. For all calculated divisions, so it's L-1 divisions, we calculate the mean value. It's just like the mean value of the subsample. In the next tables, we have all possible left and right divisions and their corresponding mean values. Okay, so this table corresponds to possible right divisions, yeah, of our tree. So, and we start from the first one, where the first entry is allocated to the left part, yeah. So it means that we have actually the diagonal matrix representing possible ways on how the initial data sample can be divided. The lower row, yeah, gives us the calculation results of the mean values of the right of possible right divisions. So the same procedure is carried out for the left parts, and again for the left parts we calculate the mean value. The first one, so it's quite understandable. Yeah, so we have just one entry. For this reason, the mean value equals to this entry as well. Okay, so for all left divisions, we calculate deviation from mean value of the subset. It's like for S1 left, yes, here, minus S1 mean S1 left. Like moreover, we get the sum of squares of this deviation for right and left parts using these and these formulas. For all the divisions, we calculate sigma left and sigma right, yes, which are provided here, and divide it. And divide the sum of sigma left and sigma right by the number of elements in the sample. So in the sample, let me remind you, we have 17 elements. For example, for the first left division, actually we have 0. Because the mean value equals to the only existing entry in the first left division. For this reason, we have this 0 deviation, and square deviation of 0, yeah, will also be 0 as well. And right division is provided for the right entries, yes, and the vector containing the right entries of the subsample is given here. Yeah, and here we have the mean value. So we calculate the sum of squares and get the final result of 633,662. Yeah. Actually, and for the first, yes, for the first right division, so we calculate the value of delta. In the next tables, we have deviations from mean and sum of squares of these deviations for left and right parts, and actually calculated values of delta for k equals from 1 to L minus 1. So this slide, this table illustrates us the deviations of the entries of the right, yes, of the right subset from the mean value in this subset. And here we'll calculate, yes, the squared sum of the deviations. So the same we have for second, third, fourth, etc. So please feel free, yeah, to check the calculations provided in this table. And the same we have for the left part. As far as for the first left division, we have 0 deviation from the mean value because we have only one entry in the subset. It means that the square deviations will also be 0. Yeah. And again, please feel free, yeah, to check the calculation results of all of the sums of the square deviations for the presented subset. So we just analyze all possible scenarios, yes, so on how this data set can be divided, yes, to form the left and the right part of the decision tree. Okay, so we calculated delta, and what is really important that minimum delta corresponds to the optimal case of dividing the sample into two parts. And for the given case, it's number 6. As a result, we divide initial data sample into two parts. And this one corresponds to the left part, yeah, and this one corresponds to the right part. But what about decision rule? Because in each decision node, yes, of the decision tree, it's like here, yep, or here. So we have to state a special condition. Actually, the decision value is the feature X. In our case, it's irradiation at the border of the atmosphere. So by which we divide the sample into two parts, and this feature is calculated as a mean between last value in the left part and first value in the right part. So in the given example, X split is equal to 217, and the corresponding marginal values of X, yes, are provided here. Well, for this case, for all the input variables X which are lower than the value of X splitted, the algorithm will calculate the output as a mean of all outputs of the left part. And the mean of all outputs of the left part is provided here. And actually the same goes for the right part. And it means that for all the inputs that are lower than X split, the algorithm will calculate the output as the mean of all outputs on the right side, on the right branch of the decision tree. So, and the calculation result is here. Okay, so as a result, we get the decision tree of two levels. So here is the input, and here we see the decision rule, so the main condition. Okay, so the obtained decision tree gives the opportunity to calculate the output, yes, for each of the features X, and the outputs of the regression tree are given in the table. So you may see that this part, yes, of features provide us with the output corresponding to the left branch of the decision tree. So these inputs provide us with the result corresponding to the right, yes, branch of the decision tree, and the last one again to the left branch of the decision tree. The algorithm acts as a step function describing the dependence of the measured irradiance from solar irradiance at the border of the atmosphere. So this step function, yes, is presented at the diagram at the right lower part of the slide. In order to add another level to a decision tree, we should provide the same actions both for left and right parts. So actually, as a result, we get the division of the initial data sample as presented in the subsequent tables. First of all, we take left part of the second level, and we are expected to transform this part to the left part third level and right part third level. And the same goes for the right part of the second level, which is expected to be divided into left part of the third level, yes, and right part of the third level one more time. So we skip the detailed calculations of the next level of the decision tree because, well, practically it acts in a similar way. So please feel free to choose the branch, yes, and check the calculation results. Well, the resulting decision tree looks as follows, and in this decision tree, yes, so we have three values, and we have performed decomposition, yes, of level 2 left part into level 3 left part and level 3 right part. So, and the same was performed, yes, for the right part of the subsample as well. The resulting decision tree has a little bit different decision rules. Actually, we kept the same decision rule, yeah, for the right part, right branch of the decision tree. And for the left one, we have new decision rule, new condition, and we produce another output. So as far as we have introduced extra levels into the decision tree, so we made the decision process more smooth and more flexible. And here you see the function, the step function here, yeah, illustrating the approximation mapped to the axis of irradiance at the border of the atmosphere and measured irradiance with the help of horizontally installed pyranometer. Okay, so the final result, yes, for the sample day for the initial data set is provided in the chart diagram at the upper side of the slide. Actually, the calculated decision tree, B1, it's like the first basic algorithm, and it is added to the composition A0, yeah, and we remember that A0 equals to 0 because we've initiated algorithm with this step. And we add the basic algorithm with some certain variable, which is called step length. In this example, step length is assumed to be 0.1. Actually, then the response of the composition A1 of X1 would be as calculated here in this slide. Similar calculations may be provided for the other features X, and actually at this stage, the first iteration of the calculations is finished, and these results of the first calculation, they naturally serve as initial data for the second iteration. So we limit the number of iterations to stop the algorithm, but anyway, so on the second iteration, we are going again to create a new basic algorithm, but which is tuned to correct the errors of the first iteration, the results of the first basic algorithm. Well, we are smoothly coming to lecture outcomes, and I would like to start with saying that decision trees is a really widely spread concept for machine learning. Yeah, so and decision trees are used everywhere in classification and regression tasks. As far as the decision tree is a really weak maybe concept, because a single decision tree, so if having low number of levels, yes, so would likely act as random guessing. But if you create a very deep decision tree, you have the risk to overfit the model. Yeah, and for this reason, ensemble algorithms, which combine different decision trees together, like random forest, which combine simple decision trees by taking the mean, yes, of all possible outcomes of all of the decision trees. So by doing so, we provide a strong solution. So we create a strong composition of weak learners. So it's like, group intelligence. Complex decision tree structures, they require high computational capacity. For this reason, when you implement ensemble algorithms, please limit the level of the weak learners. Yes, so the level of the decision trees. So if it's taken too big, yes, so you are really likely to overfit the model. For this reason, moreover, yeah, so if it's too big, you will require really long time because it requires high computational capacities. I really hope that the example with irradiation, with solar irradiation decision tree creation was effective and useful for you. And I hope you've got the basic idea on how the regression trees are formed. And actually, at this step, just imagine that for a random forest, for instance, we have 1,000 decision trees, maybe 10,000 decision trees. So, of course, such algorithms, I mean ensembles of decision trees, are not possible to be checked because it's like a black box. So you will never be able to make these 10,000 of decision trees. So you had only one, the task associated with one decision tree creation with a very small data sample. But just imagine what happens if you create 10,000 of decision trees. But anyway, I hope this simple example was really useful, yes, and threw some light on the process of regression trees creation. Thank you very much for your attention. This was lecture dedicated to decision trees and, well, with a special focus on the project case of the summer school. It was Stanislav. Thank you. Bye-bye.